Here is the math that decides whether a billion-dollar chip program makes money or loses it. A modern AI accelerator program ships 10 to 20 million die per year. The cost to make one of those die at TSMC's 3-nanometer node is around $8 to $12 in wafer costs. The yield, meaning the fraction of die on each wafer that actually pass test and gets shipped, is somewhere between 60 and 80% through the life of the product. If yield improves by 1/10 of 1 percentage point, just a fraction of 1%, on a 10 million unit annual program, the math is straightforward. 10,000 more die per year. At an average selling price of $500 per accelerator, that is $5 million of pure margin per 10th of a percent. Across a 5-year product life, $50 million from 1/10 of 1%. This is what yield engineering decides. The role that hardly anybody outside the fab industry talks about, and that nobody in the AI hype cycle has ever named, and that single-handedly decides the gross margin of every advanced chip in the data center. And which two layers of the supply chain quietly profit the most from the fact that yield never stays still? The yield engineer is the person who tracks every die that passes or fails on every wafer, finds the patterns in those failures, and tells the rest of the program how to fix them. The role sits at the intersection of the foundry, the design team, the test floor, and the customer. It is one of the most data-heavy disciplines in the entire chip industry. A modern fab generates roughly 100 million data points per day from inspection, electrical test, and process control. The yield engineer's job is to find the signal in that ocean of noise. 4 walls define the work. Wall 1 is the wafer map, looking at the spatial pattern of failing die on a wafer and recognizing what process step caused the failure. Wall 2 is the kill ratio Pareto, finding the 5 defect modes responsible for 80% of yield loss, so engineering effort goes to the right place. Wall 3 is the yield excursion, what happens when yield drops 10% overnight and the entire program calendar depends on finding the root cause within 48 hours. Wall 4 is the customer negotiation, when the contracted yield was 80% and reality is 65. Walk through them in order. Wall 1 is the wafer map. The yield engineer opens a piece of software that shows every die on a wafer color-coded by pass or fail. A wafer holds anywhere from a few hundred large AI accelerator die to several thousand small ones. The pattern of where the failures cluster on the wafer surface is the most important diagnostic signal in the entire fab. A ring of failures near the wafer edge usually points to chemical mechanical polishing, non-uniformity in one of the metal layers. A cluster in the center suggests a deposition uniformity problem in chemical vapor deposition. Random isolated failures spread across the surface usually mean random particles falling onto the wafer during one specific process step. Diagonal stripes mean stepper field misalignment, which is a lithography problem. Concentric rings mean implant non-uniformity. Each pattern is a fingerprint. A senior yield engineer can look at 1,000 wafer maps and identify the signature in seconds. Pattern recognition models from PDF solutions and synopses can classify the obvious patterns automatically. What they cannot do is decide whether a new, never-seen pattern is a real systematic issue worth chasing, or random clustering that will look different on the next batch. That is a judgment call. It costs money either way. Wall 2 is the kill ratio Pareto. The yield engineer takes all the failures across a month of production and asks one question. Which defect modes are responsible for the most yield loss? The output is a sorted list. The top 5 defect mechanisms almost always cause 80% of the loss. Front-end metal, short. Back-end via open. Bridging defect on metal 3. Embedded SRAM, single-cell fail. Vias missing in the redistribution layer. Each entry has a percentage of yield loss attached to it. Each entry also has a different cost to fix. Some are foundry process problems that take weeks of TSMC's process integration team to characterize and adjust. Some are design vulnerabilities in the customer's own layout that require a metal mask engineering change order. Some are equipment-induced and can be fixed by tuning a recipe parameter in a single day. The yield engineer's job is to align engineering effort with the top of the Pareto. PDF solutions and Siemens EDA calibrate tools rank the entries automatically. What no tool decides is which entries are worth a medal only a respin of the customer's design, and which the customer just has to absorb because the schedule does not allow another tape-out. That conversation involves the program manager, the customer's product team, and a spreadsheet showing yield improvement versus quarter of revenue. Wall 3 is the yield excursion. Tuesday morning, the overnight test data comes in. Yield on the current production lot is 63%. Yesterday it was 76. Something changed. The entire program calendar now depends on finding the root cause within 48 hours, because every additional day of production at the new lower yield costs hundreds of thousands of dollars in wafer cost that will not return revenue. The yield engineer opens the wafer map for the affected lots. The failure signature is new. Diagonal lines of failing die that were not there last week. They cross-reference which equipment processed the lot at which step. 6 lithography tools, 12 dry etch chambers, 45 different processing recipes. Each combination is a search axis. The KLA inline inspection data shows particulate contamination on metal layer 4. They trace the metal layer 4 deposition tool. One of the chambers had a maintenance event on Sunday. The replacement target wafer position was slightly out of spec. The recipe is adjusted. The next lot ramps back to 75%. 2 days of detective work. $40,000 of intermediate yield wafers shipped to the bone pile. The customer is told it was an upstream excursion, handled with no schedule impact. No tool runs that triage on its own. Wall 4 is the customer negotiation. 6 months into volume production, mature yield was supposed to be 80%. Reality is 65 and stuck there. The contract with the customer specified 80% as the basis for the per die price. At 65% yield, the chip company is losing money on every wafer that ships. The yield engineer's job is to lead the technical conversation with the customer's engineering team. What can be moved out of the kill bin and into a downgraded performance bin instead? Modern AI accelerator products bin by frequency, by core count, by SerDes lane count. A die that fails the top bin spec might still be good enough for the middle bin, sold for 30% less. A die that fails the middle bin might be good enough for an automotive variant at 50% less, but a guaranteed buy. The yield engineer rebuilds the wafer probability distribution with new bin boundaries. The customer's product team validates the lower bin parts against their reference platforms. The contract gets amended, the per die price gets reset, or the customer walks. That is a business call wearing yield clothes. The yield engineer holds the technical credibility that makes the customer believe the new numbers. No AI tool has that credibility. So why does yield stay so hard in 2027 with AI tools sweeping every other corner of the chip design world? 3 reasons. Reason 1, yield is an integrator role. The cause of a yield drop can be in the foundry's process, in the customer's design, in the test floor's contact resistance, in the package, or in the equipment vendor's recipe. The yield engineer is the only person whose job is to hold all 5 domains at once. No AI tool has access to all 5 data streams, because each one is owned by a different company with strong reasons not to share. Reason 2, pattern recognition still needs years of domain experience. A senior yield engineer who has seen 1,000 wafer maps can spot a new failure mode in 5 minutes. The same data shown to a machine learning model trained on the prior 1,000 maps will confidently classify it as something it already knows, because it has no concept of novelty. The senior yield engineer recognizes when they are looking at something they have never seen. Reason 3, bin migration is a customer relationship decision. Renegotiating bin boundaries with a customer requires trust built over years of accurate technical communication. AI tools do not have customer relationships, so who profits when yield never stays still and the engineer is the bottleneck? 2 layers. Layer 1 is the yield data analytics software, almost entirely owned by PDF Solutions. They sit between the fab data and the yield engineer's analysis, with a direct API into every major foundry's defect database. Software-grade gross margins, roughly 70%. Almost nobody outside the fab industry has heard of them. Layer 2 is the inline inspection equipment, KLA. Every wafer that passes through an advanced node goes through KLA inspection tools at multiple steps. Every defect signature the yield engineer chases starts as a KLA image. The hardware ships at premium pricing with no second source for the most advanced toolsets. PDF takes the software margin. KLA takes the hardware margin. The chip company writes both checks every quarter for the life of every advanced product they ship. That is yield engineering, the role that hardly anybody in the AI hype cycle has named, and that decides the gross margin of every advanced chip in the data center. Real Silicon Jobs is the series on the chip engineering roles AI cannot replace. Subscribe to see the rest. Next episode goes inside the system architect, the role that decides what the chip is supposed to do in the first place, 3 years before any of the other engineers in this series ever see the project. Watch the numbers.